Thanks for a nice introduction. This is Anthony, and today I'll be talking about random matrices. So we start with this big question: what are quantum computers good at? So you all probably have your own answer to this question, whether from a theory or more practical point. Let's just quickly refresh what examples we know. So we know factoring is very good. This breaks RSA. And then if RSA has been classically secure, then it is a very good example of what quantum computers are good at. Okay. However, if you think about applications, maybe this is not the only application you care. Maybe you want more like an average case, like a widespread application, so that you can profit from it, perhaps. Then then the second task might be more interesting to you, which is quantum simulation. This is a very, very old idea of Richard Feynman, who says that you can simulate quantum system on a quantum computer. And right now, this has been a very promising, or at least very popular candidate for strong applications of quantum computers. Okay. However, on the theoretical side, it's not very clear about what kind of advantage are we expecting. Okay. There's strong intuition about it, but it's not theoretically it's not been clear. And that will be our main focus for today. I believe you have seen these related quantum advantage or quantum supremacy arguments throughout the conference. Today we'll not talk about them, and we'll only focus on this motivation from quantum simulation. Okay. As a quick recap, quantum simulation is the task to simulate quantum system using a quantum computer. And an example, a question you can ask is, say, what's the ground energy of carbon dioxide? Okay. And to do that, there are several pretty standard subroutines. You prepare the state, you do time evolution, and then you do measurements. Okay. And the last two, time evolution and measurements, has arguably been well understood. They're standard approach to them, they're good error bounds. But for the state preparation part, it has been extremely mysterious. Okay. So in fact, if you look at some of the proposals that actually lays out the actual cost of simulating quantum chemistry or materials, we realize there's just some unknown parameter that's associated with state preparation. Okay. In practice, this could be a really big problem. You don't know whether you should multiply your cost by 1,000,000 or 1. Okay. Could make a big difference. And it turns out this mystery comes with a good reason. It's because the subject itself is very rich. Okay. So formally, let's consider the following question. Someone gives you a Hamiltonian, and you're asked to prepare its low energy state or the ground state. Okay. Well, if you're from complexity, you immediately see this would be a very hard problem in the worst case. Okay. So it could be QMA hard, and means that we don't expect even quantum computers to solve it efficiently. That seems a little pessimistic if this is a good application of a quantum computer and it becomes very hard. But based on physical intuition, you might guess that if you put on your physicist hat, you might think that thermodynamics is on our side. It's going to help us because physical systems are naturally in their ground state or thermal state in nature. And if you think nature is performing some kind of quantum computation, then perhaps most physical systems are actually quantumly easy. Okay. So on complexity side, this is looking for some kind of average case statement. So there are lots of intuition about it if you ask a physicist. However, just to make this boundary between the worst case and the average case, or easy and hard, it has been very, very mysterious. Okay. And there are all kinds of obstacles. The first one, theoretically, you're just not hoping for a general proof. So you have to make good assumptions. You have to restrict your cluster of Hamiltonians. Empirically, we don't actually have a quantum computer to play with, so we don't have a large-scale quantum data to think about to gain intuition. Okay. And in fact, in some recent numerical attempts, there are even pessimistic signals on how good adiabatic algorithm may perform in practice. Okay, this is a case study, but okay, this is what it is. Okay. So you see already there's a lot of red fonts. There are a lot of pessimistic signal here. But this is not the only problem. On the other side, we still have to worry about classical hardness. Right? And hardness is always difficult to prove. But people will just keep coming up better and better classical algorithm approaching your quantum many problem. Series C, we have been restricted into this tiny region in the middle. We're being sandwiched by quantum easiness and classical hardness. It's very hard somehow on both ends. Okay. And right now, there's not really a big family of convincing Hamiltonians tell me that it should lies in this middle part. Right. Okay. In a slightly different context, a very similar story is also present and when you talk about dequantization and these linear algebra tasks. Okay, so it's not quite a context we have for today, but I just want to quickly mention that a lot of linear algebra tasks actually also becomes classically easy if you make some good assumptions, and it also rules out a large family of matrices or the kind of things you do with linear algebra. Similarly, we have restrict our potential quantum advantage into a tiny, a much smaller kind of matrix, which have to be high rank and with high precision. Okay. So far we have seen a lot of pessimism. So then we ask the following question to guide ourselves. Is there a family of classically non-trivial Hamiltonians? Okay, whose low energy states are provably easy to prepare? Okay. And the answer we give today is sparse random matrices. It's actually quite a big family of Hamiltonian that has this property. So to give a bit of warning, this smells a lot like a reverse case quantum advantage, but strictly speaking, that's not what exactly we have. Like we don't have this classical hardness proof. Instead, we say it's classically non-trivial. So we're very careful about our wording here. Nevertheless, this is what we're able to prove. And I would say what's worth emphasizing is that we find a pretty big family of average case Hamiltonian that has this property. Okay. Okay, so now that there's a guiding question, before we present our main model, let's see what existing model in the market are doing, okay, and why are they not fitting into our question? Because there are already a lot of Hamiltonians that you can think of. A very natural family of Hamiltonian you can construct are just putting random signs on Paulis. Now, these are natural analogs of their classical problems, like spin glass and constraint satisfying problems. And let me just instantiate what we know about these Hamiltonians. Okay? So suppose you want to consider the difficulty of producing a low energy state. So the horizontal axis is the energy, and you want to be as close to the ground state as possible. But then turns out, if you're only asking for a constant approximation of the energy, it's actually efficient classically. They're actually product state for it, and you can find them very quickly. Therefore, if you want this problem to be more quantum, you have to go to lower energy. You have to get very close to the ground energy. But then you run into another problem, that this problem becomes very glassy, at least heuristically. And that would almost mean that this problem is quantumly hard. Okay. So somehow for this very natural random Pauli model, it's kind of the opposite of what we wanted. Okay. So unless we know what's happening in this middle, this problem, this family of Hamiltonian is not going to help us. Okay. So somehow things get a little better if you switch Paulis with fermions. So perhaps you have seen this model sometime in your life. This comes from the black hole community as model for quantum black holes. Okay. Whatever the physicists said, let's just keep in mind that what they told us is that this model becomes chaotic all the way, even near the ground energy. Okay. We can ask, what do we mean by chaotic? This physicist wording. But then if you believe chaos means thermalization, then maybe it is indeed easy, even all the way down to ground energy. So this sounds pretty promising. However, the best proof we found is by Hastings and O'Donnell very recently, and for them it's only possible to prove up to a constant approximation ratio. That is quantumly easy. Okay. Unfortunately, it seems very difficult to push further beyond a constant approximation, and the physics argument at low temperature is very heuristic, is very uncontrolled, and we really don't know what's happening near the ground energy. So this sounds like a pretty promising example, but right now it seems technically there are some barriers there. Okay. So lastly, if you insist on getting understanding of the entire spectrum, or at least near the ground energy, here's an example, which is a random matrix. Okay. So there are all kinds of random matrix family you can construct. This one is GUE. So it's essentially as Gaussian as you can up to the Hermitian constraint. And famously, perhaps you have seen the semicircular spectral distribution for these Hamiltonians. Okay. This seems pretty nice because we know the spectral distribution. Okay. However, there's a very, very big problem in terms of its complexity. It's because it has way too many input parameters. Right? So if you're willing to pay the exponential cost, you might as well just do exact diagonalization. Right, so somehow the complexity aspect of these random matrices are like not interesting in terms of quantum versus classical. Right, so these are the family of Hamiltonians we found in the wild. And now we're going to construct our own, okay, that would fit this question. So what is it? And here is the Pauli string ensemble. It is a family of random Hamiltonians. Okay? It has randomness. It's constructed randomly by picking independent sum of random Pauli strings with random signs. Okay, so these strings are chosen uniformly from all possible Pauli strings, and the signs are uniform random. You take m of them, sum them up, and normalize by root m. Okay. The resulting Hamiltonian is highly non-local. The strings are going to be very long. It's going to be very non-commuting. From linear algebra, you can think of it as a sparse matrix. Right? It is m-sparse, since there are only m Pauli strings. Okay. And this is our ensemble. We'll show that this ensemble is quantumly easy all the way to ground energy. Okay. And as a complementary result, we also have circular lower bounds that essentially matches the algorithmic cost. Okay. So the circular lower bound will be our evidence for classical hardness. Okay. So let's look a little more carefully on the quantumly easy part. The theorem states that the low energy states of the Pauli string ensemble has low quantum complexity. There's an efficient algorithm that founds this low energy state to arbitrary good approximation of the ground energy. So you see the scaling is 1 minus epsilon, and you have the freedom of making epsilon as small as you want. Technically, we should be careful about there's a order of quantifier. There's order of whether you choose m and epsilon first. We believe is a technical artifact, but right now this is what you have. Okay. Further, the algorithm that founds these low energy states is actually the most simple one. It's just phase estimation with the maximally mixed state. Okay. Lastly, our algorithm or our entire theorem works in an average case. It works for this family of random Hamiltonians. Indeed, in the worst case, this Hamiltonian could be all kinds of things. It could have some hard combinatorial problem, but that's not what our statement is about. Our statement only works in the average case with high probability. On the other hand, we also proved that all of these states are actually have also a pretty good circuit complexity. So it means that if someone gives you a small circuit and allow you to change all the gates, you're not going to find a good energy. Your state is going to have a very poor energy. In short, the complexity is going to grow with the number of Pauli string m. Okay? And the scaling is root m. Okay? We can contrast it with recent proof of an LTS, which has a log n depth. So we shouldn't be too quantitative comparing these two results because the setting is quite different. Okay. And in fact, here we have a lot of randomness to use, so the proof becomes a lot simpler. It's only 3 pages on this part. It's a direct counting argument. And here it's very important that we have the non-commutativity of Pauli strings that allows us to get this very generous bound on circuit complexity. So that's our main result. And let me now quickly mention the proof idea for the quantum easiness, because I think it's very crispy. So the idea is just a semicircular spectrum. I claim that the Pauli string ensemble typically has a semicircular spectrum. And if you look close near the ground state, near the edge, is actually the density remains very high. It means that if you just perform phase estimation with the maximum mixed state, there is a decent chance of finding these low energy states. Okay. So if you're just doing a few more trials, you can find these states pretty easily. Okay. So yeah, then you say, well, how do I know the Pauli string ensemble has this semicircular spectrum? So indeed, many things could have gone wrong. Your matrix could have a very wild spectrum. It could have a gap. It could have fluctuating density. This would kill the algorithm. Nevertheless, with understanding from non-asymptotic random matrix theory, we can control the fluctuations from the semicircle. Okay? Therefore, our entire technical argument boils down to the following statement. The Pauli string ensemble mimics smooth properties of the GUE. And these properties include the minimum eigenvalue and the coarse-grained spectral density. With these two properties, you can already conclude the algorithm's success fairly easily because there are a lot of states near the ground state. Okay? In other words, the exponential complexity of GUE is not necessary for the semicircle. This could occur at very, very low complexity with just very few bits of randomness, such as the Pauli string ensemble. Okay. You say, and then you ask, well, how do I see that the Pauli string ensemble should be similar to GUE, should have a semicircle? Here's a very mild hint, is that the second moment actually matches. For those of you who might be interested in the mathematical context, this lies into this universality principle. Okay. So this universality principle in probability has been there for a very, very long time. It appears in even proof of central limit theorem, proof of some sparsification of spin glass, some results about universality of random matrix theory. It has a long history. But the picture is very simple. That's exactly what we're using, is that you start with some ideal model that you know. In this case, it's the GUE. We know everything about GUE. And now you have some wild model that's not as nice as GUE, but still captures some essential properties of GUE, such as the second moment. And then you want to argue that these two models, even though they're different, they keep the essential properties the same, such as the spectral properties that's needed for our proof. Okay. Technically, the setting we have is just to consider two Hamiltonians. They're both independent sum of random matrices, and you only know that these matrices has matching moments, say for t equals to 1 to 3. Okay. And that is sufficient to give a proof, and we're able to capture this this setting entirely. By constructing a path that smoothly interpolates between these two Hamiltonians. And each time you swap these terms one at a time. Okay? So unfortunately, this is all I can tell you about the mathematical part of it. I would like to come to the end of the talk. To summarize, today we started out asking what are quantum computers good at. Then we narrowed down to quantum simulation, and then we narrowed down to state preparation. Okay. We end up thinking about this problem, whether there's a family of classically non-trivial Hamiltonians whose low-energy states are provably easy to prepare. Okay. And the family we give is a very large and simple family, which is the sparse random Hamiltonians. Okay. It's very nice in the sense that it's average case. There are so many instances of them. You can draw randomly and you get one. Okay. It's also nice in the way that it's so simple that the simplest quantum algorithm works very well. At the same time, there's a matching circuit lower bound tells you that these states are also very quantum. Okay. The underlying idea behind is simply the semicircle. And there are some technical tools that are required to control the semicircle. But this is the very idea behind why this works. Okay. And you might have many questions, like you may have lots of complaints. If you think about, if you're interested in physics, you might say I want local Hamiltonians. I don't want these very non-local Pauli strings. If you care about complexity, you might say I want a decision problem, or can you prove classical hardness? So yes, these are all very valid complaints. But they will be very interesting in future directions. And thank you.
Thank you very much, Anthony, for this really interesting talk. Do we have any questions? Thanks, that's really beautiful. What do you know about the gap in this ensemble, the spectral gap?
This one?
Yeah, in the sparse random matrices.
They're not supposed to have a gap. The exponential is small. Yeah. Yeah. That's why it works.
Yeah.
Yeah.
Hi, thanks for a nice talk. I know you said you wanted to leave this for future work, but do you have a sense of what the classical hardness of this of sparse matrices looks like? I know in the physics community, like people are very excited about like being able to do sparse SYK classically, and it seems to work very well. So do you have some reason or belief that these sorts of things are classically hard, or are you not even claiming that?
So it depends on what kind of hardness you want. Like empirically, you can like I would guess that these classical numerical algorithms always scale exponentially. So in the scaling, it's going to be poor. I mean, when you sparsify things, always get better. And theoretically, I don't know. Yeah, this doesn't seem to fit into like I guess you can construct oracles or try to use computational assumptions, but I try a little bit. It's not entirely obvious. Yeah.
Okay, thank you.
Yeah, so I was wondering about this statement that you made about that this ensemble that you consider, it only mimics the smooth properties of the GUE, you said, right? So should I take that to mean that you can establish some sort of hard lower spectral bound? Because I mean, usually in the GUE you have this Tracy-Widom distribution at the edges, right? Which is in principle also, I mean, can extend indefinitely. Are you saying that this is not present for the particular ensemble you consider here, or?
So empirically, somehow, I think the random matrix behavior are way more robust than we can prove. So the things we can prove are if you can write down some kind of polynomial function of it, such as p-norms or some resolvent. If you can write down any smooth function, then I'm pretty sure it will behave similarly. But if you're asking something like, oh, what's the refined level spacing, or like these very tiny details of these fine-grained properties of a random matrix, I believe it's true, but it's very hard, very, very hard to prove.
But then, so you're saying that this random matrix behavior is very robust, but that's not the case then apparently for the Tracy-Widom distribution that you usually have at the edges of the spectrum.
And So I assume the distribution you're looking for is like exponential, like it's very refined, right? It's about 1 over dimension kind of scaling, right?
Right. Yeah.
And that I'm not sure if that would happen for these sparse random matrices, and in fact expect it will have a larger fluctuation because it doesn't have that many randomness.
So you expect to see larger fluctuations at the edges?
Yes, yes. And if that's true, so I don't know if it's true, but I expect it to be true. But if that's true, that would be some kind of decision problem you can ask.
I see. Okay, thanks.
Sure. So you mentioned that a physicist might be more interested in local Hamiltonians. Have you thought about a reason why anyone would be interested in these? Like, is there some problem with this maps nicely onto this, or?
So the question is, why is this the interesting model?
Like, is there maybe anything? Is there maybe any other problem that this solves, for example, or like any interesting application?
This model is what it is.
Okay. That's what I thought. Thanks.
Yeah.
Okay, so we have another question there.
So with the kind of back to local physical models, I mean, in principle, there are models that people kind of on the folklore level, they believe them to be hard. Classically, let's say some kind of two-dimensional critical models, you quickly run into the strange metals, whatever, you quickly run into things that people believe to be hard classically. But at the same time, people give these arguments, for, let's say, from adiabatic quantum algorithms or maybe from like simulated cooling. So what is the missing part there from your kind of rigorous perspective? Like maybe kind of some lower bounds on like circuit, or like can you comment on that? Or maybe you don't believe that they're classic quantumly simulable. So can you a bit comment on those kind of ideas?
So you're asking how this approach would apply to local Hamiltonians?
No, I'm more asking like why local Hamiltonians that are believed to be classically hard and believed to be quantumly easy through adiabatic algorithms or through simulated cooling, not kind of an answer to your question, and not why not make that a bit more rigorous rather than, you know?
Yeah. I think people have tried for a very long time, but just to prove adiabatic algorithm works, I think it's quite tricky. And now I think one way to go around that is to look at other algorithms like Gibbs sampling, like more like quantum Monte Carlo methods. But I think right now I would say that we don't know very much about adiabatic algorithm. It just becomes like a gap problem again. And perhaps we should look at other kind of quantum algorithm to prove guarantees.
Thanks.
Yeah.
Okay, so let's take the last two questions.
Hi, very nice talk. So I think this relates to your open question about decision problem, but you know, if you can prepare this state that you think is, you know, or you have evidence that it's non-trivial or has non-trivial circuit complexity, is there a feature you can extract from the state that you don't know beforehand to how to compute efficiently classically? Because it seems like the energy, you know what it's going to be. And
yeah.
So is there anything that you don't know what it's going to be and you can measure from the state?
Yeah. Yeah. So these are two candidates. So as you said, things will concentrate because the random matrix theory is a semicircle. However, it seems that for these not so random like polystring ensemble, there will be fluctuations to these exact values. And these fluctuations seems to be polynomially small. I don't know how to prove it, but if that's the case, that would be a candidate problem to ask.
But I guess just a follow-up is, can you resolve those fluctuations with the algorithm that you have?
So I guess if you actually have a quantum computer and do it, I think it's yes, because you require like inverse polynomial precision. You can just pay that polynomial cost. But to prove that the spectrum is really nice, and even like there's no like inverse polynomial gap in this spectrum, that will require further developments in random matrix theory. So practically, I think yes, but like theoretically, there's still like some details you have to root out for that to work.
Thanks.
Okay, so then let's maybe conclude the session by thanking Anthony again and thanking both the speakers.